All right. Good morning, everyone. It's a pleasure to see you guys here today. I think we're going to have a few more participants trickling in, but wanted to get started here. So thank you for being here today. Welcome to the Indoor Ag Science Café. Just going to go through a few details about this program that we've been running here. We have some upcoming events to share with you all. First today will be our speaker, Dr. Chieri Kubota. She's going to talk about growing leafy greens in a low pH hydroponic solution to manage root rot disease in hydroponics. And then in April, we have a very exciting international speaker, Dr. Ryo Matsuda, who's going to talk about optimizing productivity of plant-made pharmaceuticals under indoor controlled environments. And just want to note that that time will be 1 hour earlier than our usual 11 a.m. Eastern time because it's an international speaker, and it'll be somewhere about 11 p.m. there in Japan. Of course, if you want to find all of our upcoming events or want to suggest any speakers or share any feedback you have for us, you can go to the website in the top right corner, the scri-optimia.org website, and there you'll be able to find a calendar list of all of our upcoming events, and of course sign up for the email list if you are not already on that list. One other thing that I want to bring to your attention is our ongoing effort to provide information to you guys on the basic knowledge of indoor farming, everything from the background to plant responses to crop-specific production management and economics. It's been an ongoing effort of this OptimIA team to share this information to you all and make it available. You can find this information at optimiauniversity.org, and there you'll see quite a few lectures and short videos that are going to give some background into these various topics and more. And of course, you can find previous recordings of the this Indoor Ag Cafe series on the other website listed, and I'll post both of these websites in the chat so that you can easily access those. All right, and so for today, it'll be two parts. Part one will be Dr. Kubota's presentation, and then part two will be a Q&A discussion. So during the discussion, you are welcome to put questions in the chat, or you're welcome to unmute and ask them directly to our speaker. That part will not be recorded, so if you want to stick around for the Q&A, you won't be able to find that elsewhere, but the presentation today will be recorded and uploaded later on so that you can share this presentation with anyone you like. All right, so I'm going to stop sharing here, and I'm going to turn it over to Dr. Kubota to give her a presentation today.
Great. Thank you, John. Excellent introduction. Hi, everyone. I'm Chieri Kubota, professor at The Ohio State University. Let me start my presentation. There you go. Okay, so today's talk is going to be about our research program. I usually use this Indoor Ag Science Cafe platform for educating basic concept, but I decided to share some of the research outcomes because this is something we think is quite exciting and potentially a good approach to mitigate the leafy greens disease issue. So I'm so excited to share this. All right, so before going into the specific topic today, which is low pH approach for the leafy greens, I'd like to just show the list of programs we have in my lab, controlled environment, physiology and technology lab at The Ohio State University. We work on varieties of things. Some of them are leafy greens, optimization of production. Some of them are sort of interface area, vegetable grafting, connecting open field production with greenhouse propagation. And then some of them are fruiting vegetable or fruiting crop production, like indoor or greenhouse strawberry production. So we do a lot of work. Most of the projects, or all of the projects, I would say, is a problem solving. So we define the problem, and then we select the scientific approach to solve the problem. And then the new one is the data-driven high wire tomato crop management, which is a collaboration with engineers and computer scientists. So I'm so excited, opportunities we have, and then potential contributions to the industry, because I want it to be useful in terms of research capacity and outcomes. Okay, so that's enough for my introduction. So I'd like to acknowledge 3 past graduate students, former graduate students who were involved in this low pH study in Ohio State, starting with Dan Gillespie, graduated with master degree 2019, and then Gio Papio 2021, and then most recently Jeff Bates, December 2022. So it's very recent. Without them, I wouldn't talk anything today. They did excellent work, hardworking students, and then I really appreciate their contribution. In addition to that, I like to acknowledge Dr. Sally Miller. I'm not a plant pathologist, so to do some plant pathological work, understanding pathogens. Her input was just so helpful and important for us. And then also Dr. Francesca Hand and her lab members who allowed us to use her lab setup, because some of the pathogen work, I'm not going to show too much, but we can't do it in our lab because our lab is not certified for that plant pathology work. And then the last person, not least, is Satoru Tsukagoshi from Chiba University. I'm going to introduce him in a few slides later. But without him, we didn't start this experiment either. And then the supporting organizations and company for conducting this research. Again, thank you so much. All right, so today's talk is pH, and then we know that pH is important, and that's why we have sensor, and then we measure every day and try to adjust every day or every week or whatever interval you do, monitoring some case all the time, and then adjusting automatically to get a conventional optimum range, which is usually 5.5 to 6.5. Outside of this range, we know that plants, compromise growth. So reduction of growth, yield. So that's why we try not to get outside of the range. The reduction of growth or yield at low pH range, typically known as nutrient disorder. In liquid-based hydroponics, we learned that this is mostly deficiency happening in the low pH side hydroponics. If it is substrate system involving media, opposite case happens. So the toxicity, because more micronutrients dissolved in, most likely coming from substrates and dissolved in water or nutrient solution, and then plants take up, and then just showing toxicity. Two, have not been fully understood in the past. So we got confused at the beginning because of the report, toxicity report at low pH. So, but anyway, the point of this slide is pH is very important factor. And then if you don't do right job, then you get a reduced growth. And then also the pH response is not just system specific, like liquid base versus substrate base, but also species specific. And then some of the recent outcomes we achieved with my graduate student was identifying species specific pH response. That was quite important. Oh, by the way, the slide in here is an old 1942 report showing that as pH response. So why we are interested in pH, and then why we ever thought about lowering pH, because it is potential to mitigate the risk of pathogens, particularly Oomycete pathogen, such as Pythium, because literature show that, and then also one of the plant pathology graduate students in my program working on that specific, the pH effect on different Pythium species. But sort of by knowledge, acid works to, reduce the risk of pathogens. That's why you preserve your food in low pH or acidic solution. So you know that. But again, as I said in the previous slide, plants cannot grow. Therefore, we couldn't appreciate that fact that you might be able to prevent pathogens. And then Pythium is really problematic pathogen, particularly for spinach, and then also basil. And symptoms include dumping off and root rot and all that. And then if you ever grown spinach, basil, and even other leafy greens, Pythium is something you always worry about. So, so the story started, so the story started from our conversation with Dr. Satoru Tsukagoshi, who is I would say, unknown, well, very known in Japan, but not so much outside, I would say. Maybe he might offend, but he's an expert in hydroponics. And then the great thing is we went to graduate school together. So I can ask questions without, feeling hesitance, ask any questions to him, and he would always respond. And we had a conversation when I started Ohio State 2017, because I was interested in spinach, and I was wondering why spinach is not grown in US so much. Because I have seen over 20 years plus, they have been successfully grown hydroponically in Japan. So we had this conversation, email-based communication. And then I know that because I was in Japan up to 2002, up to 2002, I was in Chiba, and then moved to Arizona. But in that conversation, we went through the systems, that would allow successful hydroponic production, which is originally developed by a company named Taiyo Kogyo, which is now part of the Mitsubishi Group. But the system itself developed 1990s, and then back in Chiba, graduate students working on that system. So I'm quite familiar with that system. And then just a little bit of side story, but since last week we had a spinach conversation, so I'd like to introduce how they do. So they have a really good seed technology that would increase the germination more than 90%, so that their benchmark spinach germination over there is 90+%. And then they have a meticulous precision water management in germination, particularly the early stage of propagation. And then they use granulated rock wool substrate. They don't use media because crumbling is something they don't want. And then they do cleaning and sterilizing using a 60-degree water, circulating entire system at least 1 hour. And then all together works really well to grow spinach and then also maintain with lower risk of pathogen introduction. However, the cost of this system is quite high. So that's why I had this conversation of any other approach. And then in that conversation, Tsukagoshi-san was saying, well, there's a grower who is doing a low pH approach. And I went, low pH? How low? They go down. And then he said 4.5. And then really 4.5, how do they do that? Do they have an issue in micronutrients? And then he said, yeah, likely they're adjusting. So that's the beginning of this story. I was so interested. So I talked to my graduate student who started 2018 spring, I believe, Dan Gillespie came to my program, and then I talked to him, this is a potential project we can work on. So he took this project and then tested spinach at 4 different pH. So initially we thought, okay, let's go down to 4.5, which Tsukagoshi-san was talking about as a grower's approach, as a low-cost prevention of Pythium. And then we decided to add one more, much lower one, 4.0. I like to go a little bit wider range or extreme range so that we can see extreme reaction. And then spinach, as we expected, it's basically downhill. Lower the pH, they are not happy. So the right-hand side, you can see fresh weight of the shoot. It's linear reduction as you decrease pH from the standard, so the sort of edge of the standard pH 5.5. And then initially, we also tested micronutrient adjustment. And then we were wrong in that direction because we basically reduced micronutrients because of the information coming from substrate-based toxicity issue, right? So we thought toxicity might happen without thinking really deeply. And then that didn't work, of course, because actually we learned that it's more deficiency rather than toxicity. So the lowering micronutrient didn't work, but we could demonstrate that spinach is very sensitive to pH. You can see that very much stunted growth. And then roots do not want to come out in a nutrient solution. We tested everything in the DWC system because it's easy to manage pH because of the volume of the nutrient solution. So that's why we did everything in DWC, liquid-based production system. And then when we switched to basil, it was quite interesting because plants didn't care the low pH. So all the way to 4.0, basically we didn't see any significant reduction in the shoot mass, didn't see significant reduction in root mass. Plants are doing fine. So that gave us a quite interesting opportunity to test out the challenge inoculation of inoculation using a PCM. So for that, we reached out, plant pathologist, Sally Miller, and then learned the process of producing zoospore, which is a swimming one, the one swim around in the nutrient solution. That's why the problem, gets serious. So we learn how to produce one of the species of Pythium widely identified in a hydroponic production. Actually, it came from one of the local companies who does hydroponic leafy green production. But anyway, Pythium honey, I can't pronounce this one really well, Aphanidimatum. So that's the species we tested. And then it's a proof of concept study. We created two pH, 5.5 and 4.0. So the standard one, and then that's a low pH because basil can tolerate that low pH. And then we demonstrated that inoculated standard pH, sure enough, you get infection of Pythium. And then also we could identify oospore, which is a sign of life cycle processing. So they established the life cycle in that nutrient solution. 4.0, we didn't see that. So the clean root system, even inoculated at the same population of zoospore. And then we didn't see, of course, oospore or any other zoospores in that nutrient solution. And then if you see, let me move out here. If you see the growth, the 5.5 non-inoculated, this is a healthy standard, is non-significantly different with low pH inoculated. So that was quite nice proof of concept study. So we are very excited and then published this paper already 2020 in, I believe this one was Hot Science in ASHS journal. And then also those earlier studies gave us opportunity to look at what is going on in terms of nutrient uptake. Many macronutrients and micronutrients declined. Some of them increased too, but many of them declined in terms of uptake as you reduce the pH in the nutrient solution. And then particularly spinach, decline was huge. Basil, which didn't respond to pH, also declined some of the nutrient. I show calcium and magnesium showing the positive, the other way, showing the more decline in terms of uptake when you go lower pH. So that significant reduction as you go, as you lowering pH. Phosphorus was declined, and then sulfur was also declined in this particular case. And then the reason basil didn't respond is probably those levels are still okay, acceptable level for basil. Therefore, it was not translated into growth or yield reduction. So looking at those nutrient uptake data, we learned that mainly the nutrient deficiency happening in a low pH solution. And then key elements seems to be cations, and then most likely cation antagonism with the huge amount of hydrogen ions, which are also cations. So that's what we interpreted. And then also in addition to that, there may be some direct impact of hydronium ions or hydrogen ions in that sensitive species. So so that's what we learned. And then so the second student, Gio Papio, came in, and then he did a very small study as part of a master degree project, which was increasing all nutrient concentrations of hydroponics. So typically deficiency happening in a low pH, therefore sensitive species like spinach, we learned, our hypothesis was they could improve the yield if we provide more nutrients in a root zone. So we started thinking about how to approach, and then initially we thought we can adjust, things are declining in the low pH back to the, higher level. But we decided to do a little bit simpler way, because, when you design nutrient solution, you have to worry about synergistic effect and then competition. So we were not ready to tweak selected elements in this stage. So we decided to do just increasing everything to high concentration. So that ratio of, for example, cations and others are maintained. So it was also good, a proof of concept study. You can see in the picture, this is 4.5. We didn't select 4.0. We selected sort of moderately low pH, which is still low in a conventional standpoint. 4.5 pH for spinach. And then another one, which is a reference point, 5.5 conventional pH. And then we had a standard solution. Back then, we are using a little bit lower nutrient concentration, 1.4 decisiemens per meter. And then we increased the fertilizer concentration basically 3 times. So this 1-to-3 ratio in terms of fertilizer concentrations, but in terms of EC, because our source water influence, EC is 3.4 decisiemens per meter. But you can see that the huge improvement of the growth in pH 4.5, not so much in the conventional, because we consider that nutrient was already enough at that level, but because of the deficiency in the low pH, increasing nutrient concentration, overall concentrations helped recover some of the growth and then yield. And then you can see in the left-hand side, a whole bunch of growth parameters, low pH, standard EC, low pH, increased EC or strength of the nutrient solutions. You see the improvement, many of the parameters, and then standard pH, high EC, standard pH, standard pH. So the black one is the reference point. So we couldn't, for example, fresh weight didn't reach the same level as the conventional standard conditions, even though increasing nutrient solutions 3 times. But this gave us direction of going optimization of nutrient composition. So we were excited about that outcome GeoPapio did, and then but realized that we probably need to go back and then look at the standard response or the classifying the response of all different kinds of leafy greens, because if we want to implement the approach of low pH, we have to worry about, which one is sensitive, which one is non-sensitive crop, because typically, particularly small growers, small operations, grow more than one species using the same nutrient solution. So it was necessary for us to understand other leafy greens typically grown in hydroponics. This is a local grower setup. You see kale in front, I believe, and then lettuce, different kinds, and then basil. So they're all in the same nutrient solution. So in that case, you can't really sacrifice one sensitive one for the sake of tolerant one. So we wanted to test multiple species. So for that mission, the most recent student, Jeff Bates, I think Jeff is in the audience. Maybe he can answer some of the hard questions in the Q&A. But Jeff finished his degree December, and then this is the first phase of experiments he did. So that Dan did basil and spinach, and then we wanted to expand to different species. So we selected arugula, bok choy, kale, and lettuce. So Jeff did everything in the standardized conditions. Arugula, there are 2 species, if you know about that, but we selected Eureka species, which is a wide leaf type, instead of what's the other one? Diplotaxis? I may be wrong, the species name. But anyway, so we did 2 cultivars for each species, and then use the standardized condition in grow chamber using mini hydroponic solution, mini deep water culture with hydroponic solution, originally designed by University of Arizona Morrow Johnson program. And then we did daily adjustment pH and weekly renewal of the nutrient solution. And then we only grew up to 3 weeks just to see the response so that we can do a quickly many species in short period of time. And then it's pretty much standard conditions to grow those species. So the result was quite interesting. And so the arugula 2 cultivars, basically not as sensitive as spinach, but relatively sensitive. As you can see, pH level 4.0, roots are not growing, and then a very compact shoot. The same type of response for both cultivars. Kale, the reduction of growth by lowering pH like all the way to 4.0 was small. I think it was 10 or 20% reduction. By showing photograph, it doesn't show clearly. So that again, because it's very mild reduction. But you can argue that 10 to 20% yield reduction is huge in a commercial setup. But anyway, so this is the picture. 2 varieties, I think, the Toscano and Red Russian were tested in this experiment. Bok choy, we tested also 2. And then they are like basil. They don't care. They can grow very fast, as you know, in hydroponics. And then they are okay with the nutrient reduction. By low pH, that reduced nutrient uptake. It doesn't influence bok choy yield, just like you saw in basil in the earlier study. So this is a lettuce response, which actually Gio did, second student Gio did a small experiment which was not repeated. So I don't think we included it in thesis. So that was suggesting lettuce was maybe tolerant, and then this is also showing that there was no noticeable reduction. But if you look at carefully the yield data, it has just like kale, it has slight reduction, but relatively tolerant. So we tested two cultivars, butterhead type and then red leaf type roshai. I'm not gonna pronounce that one. All right, so to judge the sensitivity with regard to low pH among the species, we combine the data set, so the earlier data set of spinach and basil, with Jeff's recent data set, bok choy, basil, lettuce, kale, and arugula. No, bok choy, lettuce, kale, and arugula for additional species, and analyzed together by normalizing relative to the reference point, which is 5.5. So 5.5 pH level, 100% yield. So this is a shoot yield or fresh weight. And then showing the response in the linear regression. And then it shows clearly which one is relatively tolerant. So the sustaining the productivity around 10% reduction plus minus, increased, it's not a problem, but reduction up to 10% or beyond that. And then we decided to classify it this way. So the bok choy, basil, lettuce, a very low sensitivity, very tolerant to low pH, up to 4.0 we tested. Kale, arugula, spinach are relatively sensitive, moderate to high sensitivity. Spinach is the most sensitive species. So that is quite useful to proceed, move on to implementation of this approach. And then okay, so those are the sensitive species. Now take a look at nutrient uptake of those sensitive species. And then we identified 6 cations significantly lowered in terms of nutrient concentration in plant tissue. And they are calcium, magnesium, copper, iron, manganese, and zinc. And then I think zinc and one of the others, I don't remember. So only, that's right, I have a data coming up. Some of them are, type of elements, all of these species reduce the uptake. Like calcium, you can see here, everything is declining. The degree of decline is different. Of course, the arugula in this case is the fast reduction in terms of concentration. So the species specific reduction, and then the element specific pattern, some of them are all reduced, regardless of species. Some of them are different. I'll show you in a minute. But anyway, so the 6 elements we identified, some of them are macros. So the calcium, magnesium are considered as macronutrients. And then the other one, iron, manganese, copper, zinc, micronutrients. So as I said, some of the species increase rather than decrease, and then the other species decrease. So depending on the species, the response of the specific element uptake to lowering pH are different. Zinc is quite unique. It's only spinach reducing, and everyone else either maintain or increase the uptake. But we didn't consider that this is a toxicity level because we didn't see any toxicity type of symptom in those plants. So we, based on that information, very valuable information regarding nutrient uptake, we decided to design, so that's the main part, actually one of the main parts, design new hydroponic nutrient solution based on that information. So because it's very simple way of thinking, it's just like what we saw at the beginning, because deficiency is happening, then why don't why don't we just increase the concentration of the specific elements that likely causing the deficiency or limiting the growth because of the deficiency? So the standard formula we have been using over the past 2 years, EC 1.9. And then that's again, University of Arizona leafy green formula. And it has 150 nitrogen in a nitrate form, and then all the macronutrients listed here and micronutrient in this range. It's not unique solution. You can find similar solutions elsewhere. But based on that, because we are using that, we designed to have macronutrient, calcium, magnesium, which were identified as a critical decline in these species, sensitive species, kale, arugula, spinach. So we increased basically to 200% level. So they basically double the concentration of those. And then also other nutrients, iron, manganese, copper, zinc, we also did the same thing, standard formula, and then double concentration in the new formula. And other nutrients also affected because we are adding different salts, and then salts usually have cation and anion, so you have to deal with anion increase also. So for example, nitrogen or nitrate increased about 50%, and then sulfate increased quite a bit, but sulfate is known to not have any toxicity symptoms, so we didn't worry too much about sulfate. Chloride increased, but I thought we can accept this. So after all, we focused on those 6 elements, but the nutrient design is containing other nutrient up and down, or not down, up, increase. So it's a sort of whole system evaluation. So we design a solution and then compare that solution with the standard nutrient formula. So that's what we did. And then resulting EC was 2.6. So it's a little bit higher than standard. Okay, so go to the results. So the kale was unfortunately didn't respond to the new formula. So this is the conventional 4.0. Well, kale was mildly sensitive. So compared to 5.5 standard conditions, the decline of the growth is 20% or so. So it's not really serious reduction, but we didn't really improve the growth either. This one is both micro and macro adjusted, and then we have in between, I think this is macro only adjusted, so micro, so that the new formula really didn't improve the growth. So this is a fresh mass 4.0 adjusted one, and then this is a conventional 5.5 nutrient solution. So it was not so clear, or it was not really improving. Arugula actually improved quite a bit. So this is 4.0, adjusted 4.0, the new formula, and then this is the conventional 5.5. If you look at the fresh mass, you see that almost significant increase by adjusting nutrient solution. And then almost, actually non-significant difference, but we have a variation, but so that very close to or comparable to the conventional 5.5. So that is quite exciting. Spinach also huge improvement. 4.0 plants are sort of reduced growth, and then adjusted nutrient solutions we improved quite a bit, and then actually non-significant level, comparable level with the control treatment 5.5. And then you see that big improvement of the fresh weight spinach. So that's quite exciting. However, when you come up with a new approach, always have another issue. And then another issue was this small percentage. Jeff identified about 4% out of 120 plants or so tested. Stunted growth, and then regardless of the nutrient solution, but pH 4.0. And we couldn't identify what's the causal issue of that, but the plants showed quite stunted. So either nutrient toxicity or some kind of salt stress similar symptom, but the salt level is the same. So we are thinking maybe something is coming out from substrate or styrofoam panel or something. I don't exactly know. And then I don't think we analyzed the nutrient content of those teeny tiny plants either, if I remember. Jeff can correct that. But look at the roots, it just don't want to grow out. So we are thinking maybe substrate causing that, but we don't know yet. So that's something we need to go and look at. So other noticeable or notable impact of low pH. Well, first of all, good news is very low cost. Jeff particularly, and then Dan also did that, recorded how much acid was necessary to get down to 4.5 or 4.0 level. And then the cost per liter is quite low, 0.01 cents or lower. So usually in a deep water culture in commercial, per plant nutrient solution is somewhere between 4 liter to all the way to 10 liters per plant. So that's the baseline, the volume. Of course, you need to add more water, but all in all, you consider it's very small addition in terms of cost. Bad news, which I was hoping to see, but algae control was not really, achieved by low pH. I was hoping low pH might, reduce the algae, but algae seems not, worrying about pH. So you still have that issue. And an interesting thing, which is Jeff's discovery, overall flavor tends to become milder at low pH. And we actually noticed that in basil, only noticed by someone who has a culinary background, family background in a restaurant operation. He sensed that, oh, this is a little bit milder side, but everyone else is really, I can't sense. It's very mild change. But when Jeff did arugula experiment, if I recall, he said up to 4 and 4.5, it's very mild. And then as soon as it gets to 5.0, and that very strong flavor of arugula kicks in. So I thought it's very interesting. And then I looked at sulfate concentration. Sulfate concentration actually increasing with increasing pH. And then it's very interesting. Maybe glucosinolate or some compounds are changing quite a bit in pH, lowering pH, and the threshold seems to be between 4.5 and 5.0. So I have a pending study. If it is funded, we might be able to work further on arugula and then glucosinolate, collaborating with my colleague in Ohio State. So I'm hoping to share that as soon as we find something in this direction. So so as I said earlier, another student who is in a plant pathology program working on, actually pathogen side of pH response. And then it was not easy experiment because the pH changed quite a bit. But he has good preliminary study results showing that reduction of growth, different stages of life cycle of Pythium, 3 different species or 2 different species he tested. So I hope to share that results either published or in this cafe when we have opportunity in the future. So conclusion, leafy greens can be grown hydroponically in a wide range of pH, and some of the plants are very sensitive, or species are very sensitive in the range of 4.0 to 5.0. Basil, bok choy, lettuce are relatively tolerant, and then arugula, kale, spinach are relatively sensitive. And then reduction of growth under low pH is mostly due to specific cation nutrient deficiencies. And then our newly developed nutrient formula can achieve comparable yields of low pH sensitive species, specifically kale and, the other way. Arugula and spinach reached a comparable yield. Kale didn't respond, but the reduction already mild reduction. So I think I think we are okay with that. So that is quite exciting. New formula available. So if you are interested in testing this new formula, I'm happy to share the, the fertilizer recipe. I only show that parts per million today, but, to create that, you have to mix different fertilizers into the nutrient solution. And I'm happy to share that also if you are interested. However, I have a big warning here. Lowering nutrient solution pH can be low cost prevention. So that's exciting, but implementation, I think someone has a microphone. Oops, I have to mute. What I was going to say. Oh, yeah. So the implementation must be a little bit careful. So I think we need one more step because we did the small scale study. We need to do a production scale trial because some cases you have a lot of sediments in deep water culture, for example, or different substrates used or different stuff, biofilm maybe in the system. So how those things react to low pH, are they going to provide a lot more unwelcomed elements, probably residual nutrient elements to the solution? Something we need to find out by more like a commercial-based small-scale trial. So not sure how I can do this within my capacity, but if you are interested in testing, if you have a setup for small scale and wanted to try out, I'm happy to help and happy to collaborate. So with that, I think, I again acknowledge, thank to all these students, Dan Gillespie, Gio Papio, Jeff Bates, and then Sari Mira, Francesca Hand, Tsukagoshi-san, Dr. Satoru Tsukagoshi, Chiba University, Japan, and all my lab members, and then supporting company, Scott Miracle Grove, who provided scholarship to Jeff, Ohio Department of Ag, who provided funding, and then Ohio State University, who hired me, and then providing support. So thank you so much. Thank you.